Hey there, everybody. So in previous videos, we've talked about linear functions. Briefly, back in our functions unit, we talked about exponentials, which had this general form y equals a times b to the x power. All right, and here are a couple of examples of what those graphs look like. Remember, they start real low and then they shoot up, or they start real high and then they come real low, depending on what type of exponential function we're dealing with. All right, now in this video, we're going to graph them and figure out what do we have to do to recognize whether or not we're dealing with an exponential function or not. Okay, now first, a couple of important things. We got y equals ab to the x. That's the format of an exponential function. That's what we need to recognize. Now a is the y-intercept. Okay, we got two parameters here. We're going to call them parameters. We got a and b. What do they do? A is the y-intercept, like I just said. Because if I plug in 0 for x, then if I get y equals ab to the 0, knowing what we know about exponents now, anything raised to the 0 power is just 1. So this is going to go away, and I'll get y equals a. So the y-intercept is at 0a, okay? Now, the b value, that represents the factor at which this is either growing or decaying. We're going to call it growth or decay. All right? So b is a growth factor if the b value, the base, is greater than 1. Or it's a decay factor if it's between 0 and 1. So like 1/2 or 2/3, something like that is going to be a decay factor. All right, so we got two examples here. Notice how this first one is growth. All right, we know that not only because the b value is 2 and 2 is greater than 1, all right, but also because it starts real low and shoots off. It's growing. Your x's are getting bigger. Okay, notice how the y-intercept is 0, 1, because this is y equals 1 times 2 to the x. We just don't need to put that 1 there. All right, so that's growth. What about the next one? This is f of x equals 0.5 to the x. All right, so y equals, we could also write this as 1/2 raised to the x power. Now this is decay because it's starting really high, but as x increases, it's getting closer and closer and closer and closer to 0. All right, the y-intercept is still 0, 1, because this is 1 times 1/2 raised to the x power. All right, so there we see both the a value being the y-intercept and the b value being either the growth factor or the decay factor. Now, domain. Look at these two graphs. Is there any restriction on what we can plug in for our x values? Because remember, domain is what can you plug in for x. And no, notice these arrows are going off in both directions. So our domain is going to be -infinity to infinity. You may also see this letter here. This stands for all reals or all real numbers. That's what that kind of bolded R represents. Okay? And then the range deals with all possible y values. So look at the y values. Notice that these graphs are not dipping below the x-axis. So it's getting really, really, really close to 0, both of them. In the growth, it starts really close to 0 and then shoots off. For decay, it starts really high and then gets closer and closer and closer to 0. All right, but it never touches 0. It never crosses 0, okay? So the range is going to be 0 to infinity. All right, the lowest possible output you can get is really, really close to 0, but it does not include 0, hence why we have a parenthesis there. All right, and then it's just gonna, there's no limit on how on how high your y value goes. All right, now the line y equals 0, which is the x-axis, is what's called an asymptote. An asymptote. And an asymptote is a line that a graph gets really, really close to, but it never touches. All right, so if I look at this, both of these have an asymptote at y equals 0. Okay, because it's getting really, really, really close to 0, but it will never touch 0, and it will never cross 0 as it stands right now. Okay? So, and that's because it's not possible to get out 0 in this function. It's not possible to have an output of 0. No matter what we plug in for x, it's just going to get closer and closer and closer to 0, but never touch it. So, let's graph some. So we got f of x equals 3 to the x. Now remember, we could rewrite this. F of x is just a fancy way of saying y. So we get y equals 1 times 3 to the x. And I'm just doing it that way so that you can see that the a value is 1 and the b value is 3. So this is exponential growth because the b value is greater than 1. With the a value being 1, that's our y-intercept. So we can start just by plotting that point. And then we can plug in some other values. If I plug in 1, that's saying, okay, I'm going to take f of 1, which is 3 to the first power. 3 to the first is 3. So if I plug in 1, I get out 3. If I plug in 2, f of 2 is going to be 3 to the second power. Well, 3 squared is 9. So if I plug in 2, I get out 9. All right, there you start to see that growth, how it's kind of shooting upwards. Let's do f of negative 1 as well so we can get one on the other side. That's going to be 3 to the negative first. Now remember, 3 to the negative first is 1 over 3. To make the negative exponent positive, you throw it to the bottom. So if I plug in negative 1, I'm going to get out 1/3. I'm going to zoom in so I can get this a little better. 1/3. All right, so it's roughly going to be there. Now all I got to do is connect these. We'll get a different color. I'll connect these, and then this is getting closer and closer and closer to 0 without ever touching. So we got a couple points there. We connected them in that exponential curve. The domain is going to be negative infinity to infinity, or all reals. The range is going to be 0 to infinity. And the asymptote here is the line y equals 0. It's never going to touch 0. All right, what about next one? Y equals 1/2 times 4 to the x. So the a value is 1/2, b value is 4. So this is exponential growth again. So the a value being 1/2, that's going to be my y-intercept. So I can start by graphing that. I'm going to zoom in because it's going to be halfway here. And then let's figure out what the next things are going to be. So if I got f of 1, that's going to be 1/2 times 4 to the first. Well, 4 to the first is 4, and half of 4 is 2. So if I plug in 1, I get out 2. If I plug in 2 for x, f of 2 is going to be 1/2 times 4 squared. Well, 4 squared is 16. Half of 16 is 8. So if I plug in 2, I get out 8. And then f of negative 1 equals 1/2 times 4 to the negative first. All right, so that's going to be 1/2 times 1/4, which is 1/8. All right, so 1/8, or also if you could say 0.125. Now this is going to be really, really close to 0, just not quite touching 0. So we got our points there. Now if I were to connect them, we see that exponential growth. It starts really small and shoots off. Domain is all reals, or negative infinity to infinity. Range is 0 to infinity. The asymptote is y equals 0. Okay? And then lastly, we got part C. We get y equals 2 times 1/4 to the x. So the a value is 2. B value is 1/4. This tells me I'm dealing with exponential decay. All right, with the a value being 2, that's my y-intercept, so 0, 2. Now, if I plug in 1, so f of 1 is going to be 2 times 1/4 to the first. So that's going to be 2 times 1/4, which is going to give me 1/2, or 0.5. All right, so if I plug in 1, I get out 1/2. So if I plug in 1, I get out 1/2. It's going to be right there. And then if I plug in -1, I'll do that over here. If I plug in -1, it's going to be 2 times 1/4 to the -1st. All right, so that's going to be 2 times 4, because 1/4 to the -1st is the same thing as 4 to the 1st. So 2 times 4 is 8. So if I plug in -1, I get out 8. So we got 3 points there. If I connected these, all right, I get that exponential decay curve. Domain is -infinity to infinity for all reals. Our range is 0 to infinity, and we still got that asymptote at y equals 0, because it's never going to touch 0. It's going to get close, 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 but it's never going to touch 0. So here's an example of an exponential decay. All right, so last thing I want to reference is just look at what we started with, f of x equals 2 to the x, back here, and look at this one, f of x equals 3 to the x. Notice how f of x to the 3 to the x, or sorry, f of x equals 3 to the x, that is far steeper than f of x equals 2 to the x. So as our growth factor gets bigger, the steeper that exponential curve is becoming. All right, which makes sense. I mean, it's growing at a faster factor. All right, this one's only doubling each time. This one is tripling each time. So f of x equals 2 to the x is doubling each time. F of x equals 3 to the x is tripling each time. All right, so that's going to be steeper. Same thing kind of if I look at f of x equals 1/2 to the x right here, compared to f of x equals 2 times 1/4 to the x. All right, that decay factor, it's going to be a little bit steeper here. All right, we also got this a value, which is going to take into effect. But just kind of think about that a little bit. If your growth factor is bigger, or if your decay factor is closer to 1 or 0, like what's that going to do to my graph? All right, so for big parts for this first video, representing that, or understanding that the exponential function, the parameters, the a is the y-intercept, and the b is your factor, whether it's a growth factor or decay factor. All right, how to graph them, how it's getting closer and closer and closer to 0, but it's never going to touch it, and that you have no restrictions on your domain, and your range is 0 to infinity. All right, in the next video, we'll talk about how do you recognize an exponential function if you're given a table. All right, so make sure to check out the next video.